Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Ladies and gentlemen, welcome back to the Ephemeris podcast. I'm your host, Feeling, and man, has it been a long time coming. This episode right here. Um, I was on a month-long hiatus, rightfully so, because I was transitioning away from home into college. That's where I am currently, and I've gotten a new mic. I've got a new place to stay, but the content and its quality hopefully will be staying the same. The consistency, however, I'm a little bit unsure of, just because of the fact that I'm going to be busy, or anticipate to be busier than I usually was, for the last, I guess 1 to 2 years. But if that happens to be the case, that I'm much busier than usual, then I'll have to cut down the frequency of the episodes to once every 2 weeks or once a month, which once a month would be kind of sad, because at that point I've almost forgotten about this whole podcast. But anyways, that was a really, really long introduction to what we're talking about today, which we're getting into more neutron stars, actually. Our first story here is about some particularly cold ones that are helping us figure out the internal structure of neutron stars. And our second story is going to be about some huge, huge neutron stars, relatively, that are hiding behind sun-like stars, and kind of why they're so peculiar and why we're so interested in them. So, firstly, let's get into these really, really cold neutron stars that we've discovered. They have a lot in store for us in terms of their physics, but first we should start with talking about a neutron star structure and what we already know. So, for a star of such high density, which a neutron star is, we need a force that counteracts the gravity of such an object, right? Because its mass is, naturally contains gravity, and that's going to bring the star together. But to keep it in hydrostatic equilibrium, which we've talked about before on this podcast, we need some kind of counteracting force. And for neutron stars, that is neutron degeneracy pressure. I thought I'd brought this up at some point during the podcast, but I haven't. So we're going to talk about that really, really briefly here. A neutron's degeneracy pressure, arises because neutrons are fermions in the quantum physics world, and fermions are quantum particles that make up matter, like I'd mentioned in one of the previous episodes about axions, I think. And so, because they're fermions, they can't occupy the same quantum state at the same time. And what this means is essentially gravity can only do so much to compress this star full of neutrons, until quantum physics creates a degenerate gas out of the neutrons and says, no, nuh-uh, we're not going that far. And so this force that is, saying nope to gravity is essentially neutron degeneracy pressure. That's a very oversimplified way of putting it, but that is the essential idea. So neutron degeneracy and gravity make up for most of the dynamics of a neutron star, but in terms of a neutron star structure, there's a little bit of uncertainty. We don't quite know what constitutes some of the layers that exist in a neutron star. There are some very well-known ones, like we know that the atmosphere of a neutron star will have hydrogen, helium, carbon, and then in the middle is where it gets, a little bit more uncertain. You might have like some ions, superfluid neutrons, superconducting neutrons in the middle. But the core especially is the part that we just have absolutely no clue what's going on there. And so if you were to create a diagram of a neutron star, there would be some missing details. Now, a solution to this issue is the equation of state, which we currently have, and it's a state of matter model based on specific physical conditions, which, if we if you figure out which exact equation of state is correct, then we'll be able to dictate some of the structures of all the neutron stars in our universe. And a quote from one of the articles that I referenced states that the equation of state describes the relationship between temperature and pressure in all neutron star interiors, right? Because interiors is where we're the most uncertain. So, yeah, the first sort of equivalent thing I could think of that was similar to equation of state, but obviously not as complex, would be like Charles' law, right? Sort of that temperature and pressure relationship, but those are with ideal gases, so definitely not in the same realm. Now, obviously, it's, we equation of state from that point of view does sound quite convenient and seems to solve our problems here. But as I mentioned, we need to figure out which exact equation of state is correct to be able to figure out all these neutron stars. And so the equation of state currently is not specific enough for it to be a clear-cut solution. So here's where our story comes in. These three stars that are extremely low temperature, they constrain the possible inputs and outputs of the equation of state. And when machine learning scanned through the equation of state models that could accommodate for such low temperature stars, nearly 3/4 of all possible models were discarded. So that's a lot of narrowing down that these three neutron stars have done, just by themselves. Now, what we're left with is just one or two explanations for what could be going on in neutron stars, or the ones that are particularly cold. One explanation is that the creation of neutrinos through radioactive decay, which in large numbers would let out a lot of heat. The other explanation for why these stars could be so cold is the mass of the neutron star becomes so much that neutrons begin breaking down into quarks and other quantum particles. To me, or as I see it, it's just a little bit problematic because some of these like quarks and quantum particles and ions and superfluid stuff and superconductors, they're in the core of the star, and if you're letting out heat, you'd imagine that it wouldn't be directly from the core outwards. But perhaps that is a flaw in my personal perspective on this theory. It could be equally plausible, and there's probably a reason why it's been mentioned here. But those are the two possible explanations for these neutron stars that are extremely cold. And yeah, that's all she wrote. Otherwise, these three neutron stars are all good news. They've really helped us narrow down this equation of state. So the second story, as you just mentioned, 21 neutron stars that are orbiting sun-like stars. Instead of their interesting physics being the center of the story, it's more their detectability. But actually before that, there's a neutron star in the sample that is 1.9 solar masses, which is extremely huge, effing huge, I would say. If you remember, a spoon of neutron star material weighs more than all humans on Earth combined, so to get 1.9 times the sun of that stuff is almost unimaginable. Let's be real. But going back to the neutron stars that we discovered, they're hidden in binary systems with the sun-like star. I feel like I've mentioned that a million times at this point. And what's peculiar about their detectability is that they can only be noticed when they wobble their companion star back and forth. So, I don't know. You could think of them as troublesome older childs because, neutron stars are expected to be older than sun-like stars, and they're, messing with the little one, but that's up to you if you like that analogy or not. The observation of these sun-like stars and their wobbling back and forth, they're made by the European Space Agency's very own Gaia mission, which scans a lot of stars. Let's put it that way, put it very simply. And out of the billions of stars that it did scan, it only found 21 of these circumstances, I guess, or, these situations. And you might say, well, okay, if this is so rare that we only find 21 out of, you know, billions of stars, why do we know about X-ray binaries? Uh, like, surely if it was so rare, it would take a lot more time for us to realize that these systems exist. But X-ray binaries are actually a little bit different than the situations we have here. In an X-ray binary, you'd expect for mass transfer to occur between the neutron star and the sun-like star, but the neutron stars in these particular situations, they're so far from their companions that mass transfer actually does not occur. So really the only effect that the neutron star has in the system, compared to an X-ray binary, is just the wobble. And more importantly, these systems could be progenitors for X-ray binaries rather than being X-ray binaries themselves. So um, that would make them slightly different. So essentially, the neutron star is too far away to be noticed, as we would typically be able to, observe it with any other X-ray binary. So slight differences again. As per usual, we have to ask, how do we even get these systems? How do we get the binary system before the X-ray binary? Kind of a weird question to ask, but still something we usually do here. We suspect that the neutron star before it was a neutron star was much larger as an object, and it attracted a sun-like star later in its life and promptly exploded into a supernova event, which would launch the sun-like star farther away. So without the mass transfer, the star goes through a cataclysm, or the neutron star goes through a cataclysmic event that leaves us with just the neutron star, and then the sun-like star comes into the picture because it's at a perfect distance that, it doesn't get launched out of the system, but it doesn't get dragged in too close for it to be an X-ray binary. The great part of this story, if it holds true, is that it will prove the possibility of binary systems staying intact after cataclysmic events, because supernovas are, pretty huge, and you really wouldn't expect stars to hang on after such a thing. So, more ways that these neutron stars and their discovery are helpful. Perhaps it helps with solidifying stellar evolution theories on recurrent novae, white dwarf binaries, and maybe even binaries with black holes involved, but that's quite a far reach. One thing that is for certain, though, is that this would be the first time that neutron stars have been discovered purely as a result of their gravitational influence. So, yeah, pretty cool stuff here. Very unique. Quite nuanced, I'd say, for sure, but still very, very interesting. So, those are the two stories we have on neutron stars today. If you enjoyed listening to this podcast episode, I recommend you check out the rest of season 3, which hopefully will be linked at the end of this video, last 15 seconds. If you continue to enjoy the content, feel free to subscribe on YouTube, and also for our listeners on Spotify, this is slightly less applicable, but you can still check out the podcast page on Spotify if you are still interested in the content. But until next time, I will see you all later. Peace.